Welcome to Model-Based Systems Engineering. The International Council on Systems Engineering defines Model-Based Systems Engineering, or MBSE, as the formalized application of modeling to support system requirements, design, analysis, verification, and validation activities, beginning in the conceptual design phase and continuing throughout development and later lifecycle phases. MBSE is the foundation of the model-based enterprise and is systems engineering that uses digital models to complete traditional systems engineering tasks, such as architecture, capturing systems behavior, requirements traceability, performance analysis, verification, and testing. Systems engineering involves taking a holistic approach to optimizing overall performance of a design and looking at the system as part of a larger whole, rather than an independent entity. The goal of model-based systems engineering is to eliminate the seams between system definition and detailed design, eliminate the gaps between requirements and performance, as well as increase fidelity of verification and validation earlier in the system lifecycle. This is a cornerstone of the digital transformation. An important aspect of model-based systems engineering is SysML, Systems Modeling Language, the industry standard language for systems engineers. This visual modeling language supports specification, analysis, decision, verification, and validation of systems, including hardware, software, data, personnel, procedures, and facilities. USEM, Object-Oriented Systems Engineering Method, is the top-down, scenario-driven process that uses SysML to support the design and specification of systems. It provides the methodology and process for designing a system and is enabled by the SysML modeling language and the techniques of MBSE. MBSE benefits from an integrated tool environment in which all tools pull from a common source of integrated truth, thus improving decision-making, maintainability, and warfighter readiness. Using MBSE and in collaboration with other engineering disciplines like software engineering, mechanical engineering, electrical engineering, and manufacturing, we can use simulation-based verification to build, test, and validate a system multiple times virtually before having the physical product in hand. To do so, we need data that is linked throughout the lifecycle of the program. We must have a model-based systems engineering definition for the system, linked to a model-based design from day one of the program. We can link these MBSE and design models to a model-based factory so that digital twins can be used to validate our designs to the customer, ensuring that what we create matches what the customer has requested. These models will further aid system upgrades and other sustainment activities for fielded systems. The use of digital models and modeling software, rather than traditional approaches, has many advantages. Engineers can develop, analyze, and test complex systems in a rapidly changing environment. Having digital information stored in a model that updates automatically and eliminates the tedious task of providing updates constantly, freeing up the engineering team to focus on more complex tasks. This is also impactful in software, allowing for two-way interaction between models and code as the system and software are refined. Additionally, tools in the modeling system can check for errors automatically, reducing the amount of time workers spend on this part of the process. Model-based systems engineering enhances communication and collaboration by capturing information from different disciplines and sharing it in a connected model. This allows designs and requirements to be shared across functions, paving the way for successful program interoperability. Modeling tools can show the system in a variety of views for different audiences with different needs. The multitude of different views provided by the models utilized in MBSE allows stakeholders such as customers, developers, vendors, testers, and project managers to be involved in the system acquisition and design process. Data capture with MBSE allows for cross-functional perspective, spanning from design to sustainment, for product design that is built on real-time data to ensure easier maintainability and high operational availability. Applying advanced process models in combination with observed data to the engineering process is known as Engineering for Sustainment, or EFS. EFS provides the necessary foundation to ensure our designs address the complete life cycle of our products by enabling the consideration of life cycle cost and product availability early in the development phase. MBSE acts as the backbone of EFS. MBSE also gives engineers the ability to verify systems by analysis and simulation, and explore simulation in a variety of exciting ways. Models can be used to simulate various aspects of the system, to train users for different functions. Models can also be used to explore trade spaces by modeling alternative designs, while integrated tools allow engineers to analyze different mission scenarios to identify low-cost solutions. A common set of requirements within the model drives physics-based software and digital twin verification, reducing test efforts as well as identifying and fixing defects earlier in the lifecycle. As you can see, model-based systems engineering is a fundamental part of the model-based enterprise.